much more dynamic.
All right, guys, we're gonna get started. 6 o'clock. So I'm Dylan. Hensel is unfortunately not able to be here this week, but I wanted to introduce Bret Wallach from Vision Robotics. So he's gonna take it from here. Thank you, Bret.
Oops, one back. Okay, I'm president and founder of Vision Robotics, and I'll tell you all about what we do. Let's go to the next slide. So basically I'm going to do a quick one-slide overview just to kind of ground where we are. And then I'm going to basically talk about what led me to start Vision Robotics and kind of what the world was looking like at the time. Then I'm going to go through some of our technologies and products, and then I'm going to talk about the future, both of Vision Robotics and robotics in general, then open up for discussion. So Vision Robotics Corporation, we're an autonomous robotic products company based on stereo vision. We're California C Corp, and we're located on Sorrento Valley at the other end of the valley, at the north end of the Sorrento Valley Road. And we were formed in 1999, which makes us a very old robotic company, especially one that does everything based on vision. We're funded by strategic partners for various of the products, some government and private grants, and also these days product revenue even. We're currently mostly focused on agriculture and consumer robots, with a very primary focus on agriculture. Okay, so this slide is the backdrop for the history of robots and my history and everything up to the start of Vision Robotics. How many people have seen this particular graph? A couple. Okay, so the basic foundation of this slide is MIPS per $1,000. And basically, so that's millions of instructions per second for $1,000. What can you buy? So here is million instructions per second, billion, trillion, thousand. And here, of course, is the year, the time from the beginning of last century till the present. And then what we have is a bunch of data points along the way. These are, some of the big IBMs and some of the digital equipment corporations, some Apples. And it goes only till about 2000 because this was in a book published in 1999. And so, it is true that, some of the big IBMs went a lot faster than this says, but they're also millions of dollars, not $1,000. So it's kind of remarkable that over many decades, it followed a pretty good exponential trend, and still is. For example, right now, about 2015, and the high-end Intels, which can maybe stuff into $1,000 $1997, are about a couple hundred billion instructions or operations or something per second. So we're really even still following the trend to today. So then the one other interesting axis is, well, how about the processing of brains? How is that related to the processing of computers? And there's some hand waving here. It's not exact, but the idea is that while we don't know how the entire brain works, especially not an entire human brain, we do know how bits of it work, like the front end of the visual cortex, and it's sort of pre-processing. We know what it's doing, and we can say, well, that weighs so many grams, and the computer, to keep up with it, needs to do so many instructions per second. And then we can say, okay, well, if that many grams equals that many instructions per second, we can say, well, what does a spider brain weigh, and what does a mouse brain weigh, and what does a human brain weigh? And so, this shows that, sometime 2030, a little later, a little earlier, who knows, $1,000 worth of computer will have as much processing as a human. That doesn't mean that humans will, computers will be as smart as humans. They'll have the same intelligence. They'll think like humans. It just means that they'll be able to process roughly that much information. And if you look at some subsystems, it all seems to actually kind of work. So I'm going to go back up a little bit and then talk about my trajectory to get into robots and stuff like that. Well, so I was born about here, and we can see that, you know, not even a bacterium when I was born. So it was pretty tough to do anything sort of robotic-wise. And I graduated from college roughly here, so at least we're better than a bacterium, but not quite a nematode worm. And the thing is, my thesis in college was on a hybrid force position robot arm controller, and all that means is if I want to draw on a board or something like that, I want to put an even force in one direction and have position control in the other. And we were thinking, man, if I could just get 50,000 multiplies and adds a second, 50,000, we could control this robot arm. But at this point, that was basically supercomputer, and it wasn't going to happen. So even that simple thing, you know. So if you think about it, as we get into these various higher level things, some subsystems of robots have started to actually come online. For example, when we're at nematode worm, we couldn't do anything with vision. I mean, there was just no vision system that was even vaguely commercially viable. By the time we got up to spider, you know, all of a sudden you're using cameras for this or that to at least detect colors, and you know, maybe even think about an edge detector and stuff like that. And so, you know, I mean, and we had enough processing to do that. Now, if you think about something like voice recognition, like Siri, for example, you know, when we were at nematode worm, yeah, there wasn't any voice recognition at all. I mean, shortly after that, you know, we got the naturally speaking and other packages, but they still weren't very good. They required a lot of training. But now, as they're getting up into mouse and lizard, we have Siri, and it's starting to be conversational. And it seems that on the trajectory, if we had as much processing as a human, Siri would be really, really good. I mean, Siri's getting better very, very quickly. So that's, so it kind of works. I mean, it's metaphorical, it's hand waving, but it also seems to kind of make sense. So anyway, I graduated, as I said, not even to nematode worm, tried to get a job in robotics, but the entire industry basically collapsed. Because in the 70s, you know, a bunch of VCs put money into ARMs and other stuff, but there wasn't the processing to control them. You know, they couldn't do anything. And so a bunch of companies went bankrupt, and so here I am, and I basically went into you know, military electronics and software, and then some futures trading, and then finally around 1999, I sort of had a break in the action, was trying to think of what to do next. And that's when I realized, you know, we're now several orders of magnitude, about 10,000 times as much processing per $1,000. And suddenly, all these things we wanted to do at bacterium, well, we couldn't do them, but now all of a sudden, you know, we're looking at between spider and lizard. And it was pretty clear that at that point that we were going to get to lizard and beyond. So that's why I formed Vision Robotics. Wanted to get into robotics, and I knew that we could begin to achieve those sorts of functionality. So the question is, well, how did we get started? And I started with two other co-founders, and they said one of them was just really hot to do a sweeper. He wanted to do sweeper. And I said, sweeper with vision, because I wanted to be vision. And let me back up for a second. The reason I wanted vision, because the other thing that happened in the 90s is you went from huge camera, you know, tube-based things to the little tiny CCD chips. And so it's clear that was the other reason vision was coming. So I said you can't do a sweeper, because a sweeper is a surface coverage application. And it needs to go everywhere, which means the cameras are going everywhere. And basically, it's hard to keep up with the processing. Every time you move the sensors, and remember, this is orders of magnitude of processing and go, you have to basically look around and figure out what you're seeing and correlate what you've already seen. And that was going to be really tough to keep moving all the time and be able to keep track of things. So I said, no, we can't do a sweeper. And so then we tried to figure out what to do. And then one day he said, no, we should really do a sweeper. I said, fine, we'll do a sweeper. And then I sat down to design, and I came back to the same thing. Well, I can't do a sweeper because, you know, I can't be moving the cameras all over the place. So then what I realized was, well, what if I have a sweeper, but it doesn't have the vision, and I have a second unit that has the vision system. And basically, it doesn't have to move around very much. It can put itself somewhere, and then it can watch the sweeper, and the sweeper can do a large area while it just sits there and processes its back vision stuff to figure out where it is and where it's going on. And the thing is, it can easily track little markers on the sweeper. Tracking is really easy because it takes up a little tiny bit of the image. You can predict where the markers are going, and it was very processing efficient. And so we patented that, and then we said, well, let's see, who can we sell it to? And we said, yeah, let's go talk to vacuum cleaner companies. And the good news was that just about that time, 1998, the year before, a company called Electrolux came out with a little hockey puck-like vacuum cleaner, very much like the Roomba, for $1,500. So every single vacuum cleaner company took notice, and they said, robots are the wave of the future. So, you know, 3 guys off the street were able to meet with the CEO of every vacuum cleaner company we called up and presented our idea. And they said, that's great, but we want a vacuum, not a sweeper. So I said, okay, we can do that. What we'll do, instead of having you know, a separate unit, 2 separate units, we'll have the units, but they'll be attached by a hose. So it'll be a canister vacuum. Still have the markers on the cleaning head, and we still have the vision system on the main unit. And it has a bunch of advantages that you can't do with a single unit. You can plug it into the wall. It actually has a cord. And the reason it can do that is because the main unit isn't moving all over the place. You couldn't do that with a Roomba. It makes a complete model of the environment, cleans in a deterministic pattern. I'll show you a video in a second. The canister can have a full power motor. It plugs in, or you have big batteries. And a full-size dust bag, and the small clean head is actually much smaller than a Roomba, so it can get under chairs and in nooks and crannies that are much smaller than what a Roomba can access. Okay. So let's take a look at the video. So the general idea is that this goes out to the farthest point and cleans on the way back after having previously mapped the room and making a entire detailed 3-dimensional map using vision. It has a set of stereo cameras both in front and back in order to map the room. It has some headlights in case it's dark. You can see the markers on the cleaning head. You'll notice that it's a little hard to see, but it lays out cord as it goes forward, and then it picks it up as it comes back. So what you can see is that, as it goes, that it clearly knows what it's doing. It's not just randomly bumping all over the place. It actually has a model of this room and understands what's going on. So this happens to be the back room of my house, and it's actually kind of wonderful to take it home. You know, I'd be doing the dishes and the vacuum cleaner would be off vacuuming the house. Very nice. So what it basically does is it goes to a spot, and then it's going to stay there except for rotates to watch the cleaning head. You know, it knows where those chair legs are, doing detailed work. It has bumpers. The idea is that even if even with my great vision, if I'm cleaning, I'm going to go bump the wall. I'm going to go right up to the wall, so it does the same thing. You'll see that it slows down as it gets near obstacles and goes faster when it's further away. All right, let's go on to the next thing. So why will, so that one had sort of a bad ending, but we'll talk about that later because it now has a better ending. So while we were developing that, in 2004, some orange growers approached, well, one orange grower in particular approached me and basically said, we're really worried about being able to pick the oranges off the trees. If you look at the industry as a whole, there's several $1 billion worth of oranges sitting on the trees, and if they can't get them off, they're out really, they're really hurting. So yeah, he came to us and says, well, you know, I've heard all about vision and cameras. It just seems like we should be able to develop an orange harvester. And my partner and I looked at him and said, no. He said, well, wait, why don't you come up and take a look at the groves? I mean, we just felt it was really hard, and it turned out to be really hard. But anyway, he managed to get us some funding provided by the California Citrus Research Board to develop a simulation of a harvester and then the economic models. I'm going to show you a video in a second of the simulated harvester. The project has been sort of on temporary, well, semi-permanent hold since 2007. And the reason is orange trees are big, and to have arms that can somehow reach into the interior of the tree and get them are very, very large, expensive arms. And even if I had the arms, the hands, or whatever you want to call the actuator, the end effector on the arms, it has to be able to grab the orange, cut it, get it off the tree, and get it to wherever it needs to be, some sort of fruit handling system, and that's all easy. It has to do it quickly, because to be economically viable, these very, very expensive arms had better be moving and efficient every single instant. And so two things have recently happened that may solve these. There's planting smaller trees, and somebody has allegedly invented a picking hand that may be suitable. So this project may come back to life in the near future. So if we look at the next slide, so this is what was sort of our idea for design for an orange picker. This is a simulated orange grove with shapes not too terribly far off from what orange trees look like. What we decided was probably an 8-arm sort of thing, basically hydraulic platforms. I'm obviously cheating on the mechanics of these arms. And we found that if we needed to do about, every arm needed to pick one orange roughly every 2 seconds for it to be economically viable, if we could get the arm price down and stuff like that. We presented this to the Citrus Research Board just after the Spider-Man 2 Doc Ock movie came out, so we got some flack for that. But really, we did that before the movie came out, so we didn't steal it. But what we learned for the orange harvester was that the concept of scouting was very important. What I mean by scouting is to be able to understand where all the fruit is and to be able to pre-plan how to pick it. Because again, the most expensive thing on all these agricultural robots is the arms. You know, they dwarf everything else. Everything else is cheap. And so, you know, your most expensive thing, you got to keep it busy, you got to keep it efficient. And so, you know, once the growers kind of understood that general concept, they said, oh, well, that would actually be kind of useful just, you know, for selling into the market, because, you know, if they think they have 1,000 oranges per tree and it's really 1,200 oranges per tree, suddenly they have 200 extra oranges that they're going to have trouble selling. Or if they thought they had 1,000, which they've pre-sold and they only have 800, that's kind of bad too. So we looked for a while at a fruit counting scout, and that would be a product all by itself. So this is actually then a standalone scout, and what it's doing is it's counting green apples on green trees. And so this is a trick in vision. What we do is we're flashing every other frame. So what you can see is the apples go from as dark as the background to much, much brighter. And that's because anything that's spherical has a substantial portion of its surface always facing the flash in the camera. Whereas leaves, they're pointed every which way. And so, you know, that was the thing. Well, you know, there's green apples. How do you count them? And that's the trick we use there. So then the other agricultural robot we work on is a robot pruner. And so basically after all the grapes are harvested and the leaves have all fallen off, you got to cut the bramble back. There's just all these canes everywhere, and you need to cut them back to being pretty short. And you have to do it according to specific rules. And so what we did is we built a machine. This is a schematic diagram. You'll see what it looks like, and actually looks like in a minute. And it has stereoscopic cameras in the front on either side. It sits over the vine. As it gets pulled by a tractor, and the pruner actually drives the tractor, it takes images and actually builds a 3D model of the vine, and that 3D model would look something like this. From that 3D model, it decides where to put the cuts. That's the green and the red. And then the arms in the back come up to where the model has been made, knows where it's supposed to cut, and synchronizes with it. And so let's watch the end result. So this is the two arms that come back to an area that's been modeled and go through, and they just cut the bramble back. You can see that it clearly knows what's going on and which order to come in, and knows how to get around the other canes. So that's its general concept. All right. So this just repeats. Let's go on to the next one. So the robot actually, this is the pruner from the outside, and it actually drives the tractor. On the, it's a little jittery, but on the steering wheel, you'll be able to see it move. So see, there's an actuator, and so the robot's driving, and then this is the go lever right here. This is sped up because this is a slow machine. So we were well into the autonomous vehicle thing, even as Google and et cetera was working. We're going obviously a little slower, and there's a few more constraints, and et cetera. But
what year was it?
This is actually only a couple of years ago. It's probably 2011. Okay, so then the next video. So get a little bit into the behind-the-scenes technology of the clippers. So that's a typical cut. You want to take the cane that you're trying to get rid of all the way down to what's called the spur. And so the question is, how do you do that? And one of the main reasons it's difficult is because, as I said, we have cameras in front that are being pulled, and they make this model of the vine, and then eventually the arms get up to the vine. But in the meantime, everything's jiggling around, and the wind's blowing, and the vine is moving. And so what we did is we said, okay, what we need is a closed-loop controller for the arm. And on the clippers underneath, there's a pair of stereo cameras, and it allows us to synchronize with the model. So we can be 5-10 centimeters off, and it still is able to compensate. So this is actually the view from the cameras, and you can actually see the tip of the clippers in the cameras, and that's kind of important because there's touch sensors, so it knows when it's on the vine. You can see actually the tip moves relative to the camera, so it's tracking that. So it's real hand-eye coordination. So what is it looking for? It's looking, I'll let it tell us. So again, it's looking at the hook and the blade. It specifically has, these three little squares it's drawing where it thinks the hook is. The triangle, it's really hard to see here, is where it wants to put the thing it wants to cut within the blade to be cut. We also have lasers mounted on it. They're just line lasers, and what they do is they shine out, and they're geometrically mounted relative to the camera, so when we see them, they're real fast to see. We can almost instantly find the blue and the green, and that kind of grounds us. We know that there's something of interest there, and then we can trace the edges and stuff like that. So, so watch this one more time, and basically it's trying to, I can't see it, but it's trying to put that on the square, and it does it, and then it cuts it. So that's one of the bits of technology we now have is a closed loop controller, and that can be used in any sort of agriculture, and then eventually a industrial as well. And it's very, very good. I mean, it put it within about 1/10 of an inch of where it was supposed to, laterally. And if you were out there with clippers, you wouldn't be doing any better. Okay, let's go on to the next. So our final product, the one we started last but actually got into production and out into the world first, is a lettuce thinner. So quick background on what lettuce thinning is. They need a lettuce plant roughly every 10 inches. And the problem is the seeds don't all come up. Some don't germinate, some are weak, some birds eat some. And so what they do is they overplant. They plant them every, say, 2.5 inches. And so then they pop up, and now you have plenty of lettuce plants, so you have too many. And so you have to get rid of the extra ones. You have to thin them out. And what some growers realized was that one way to thin them out is to spray fertilizer on them. That same fertilizer that makes them grow, if you spray it on them, kills them because it just burns them. And you can also use herbicides and organic herbicides and other stuff like that. So basically, this one's not autonomous. Could be pretty easily, but there's a guy driving a tractor, and for each line of lettuce, there's a hood with a machine vision system down, looking down, and it drives at about 2 miles an hour, and it basically decides which lettuces to keep, which lettuces to thin, turns the sprayer off for the ones it wants to keep, turns it on for the ones it wants to thin. And if we go to the next. So here's a slightly newer version. So you can see the spray pattern. In between each of those is going to be a lettuce. There's one bed, there's 5 lines of lettuce on it. So here's after, you can see in between each one, there is generally a plant, a little tough to see. So that's the general concept. So what's interesting is that growers want to do this strictly as a cost savings. Cost them, before this is done with people with hoes. Up to 4 years ago, all the lettuce in the world was thinned with hoes, or nearly all. And it's expensive, and it's hard work, and they're having trouble getting labor, which is a recurring theme. So this is done, strictly as a cost savings thing, but turned out it had a huge number of other advantages. I mean, one is that you don't end up breaking the soil. With a hoe, you break the layer of soil, and then weed seeds can get in, weeds underneath can grow easier. The other thing is, you're taking out, with a hoe, the lettuce in between while you kind of smack the roots of the one you want to keep, so you get a lot more size variation. And it turns out that the bumpy soil affects the wind, and you get little twirls, and they'll twirl the lettuce around and kill it. So anyway, it turned out that there's a number of advantages beyond just the cost savings, and it turned out to boost yields and stuff like that. So they're really, really happy about that. And within 3 to 5 years, very, very little lettuce will be thinned by hoes anymore. Okay, so now we're going to move on to the future. What does the future hold in store for vision robotics, and in my opinion, what does the future hold in store for robotics in general? So if we look at the things we do, what happens there? So the lettuce thinner works great for lettuce. We're selling them, as I say. Hoeing will be a thing of the past for lettuce soon. So we're going to move on to other crops. Most other crops are not thinned. They're planted with with seedlings and stuff like that. But that's because one of the reasons was because they never had a really great way to thin things other than hoes. We're also looking into a much bigger market, which is weeding. Yeah, and there's just weeds come up in all fields. They come up in between the plants. How do you get to those? Well, our thinner will do that quite well. And then one of the big advantages is that there's a lot of drive to reduce the amount of chemicals we put into the environment. Most of these fertilizers aren't too terrible, they break down and stuff like that. But you know, kind of the less the better. There's the issues with nitrogen runoff and stuff like that. And then, in the whole other area is that most of the big crops are planted with seeds that are called Roundup ready seeds. And basically the idea is that your plant comes up, the weeds come up, and then you spray your field with this stuff called Roundup, and the plant is resistant to the Roundup, or impervious to it, and so it kills all the weeds. Well, of course, like, you know, there's bacterial or antibiotic resistance for some bacteria. Well, there's starting to be Roundup resistance for various weeds, and they're trying, you know, different versions of the chemicals. But the problem is there's starting to be weeds that you're going to have to hit with something else, and that's something we can do. So the robot vacuum cleaner, the video I showed you, that was from 2008, and that was done with a major vacuum cleaner company. And unfortunately, 2008 was a global financial downturn, and you probably remember. The vacuum cleaner was expensive. It was about $1,500, and it's never going to get wildly cheaper than that because it just has a lot of motors and a lot of parts. It does a really good job, and they said we can't sell it into this you know, falling market, and so they canceled the project. The only silver lining to that was all the intellectual property happened to revert to us, so that was okay. So anyway, last year another company has now picked it up, and they're redeploying it as a battery unit. But it's really the same thing. It's still a canister, it just doesn't have a cord. Because the canister is relatively large, it can have a lot of batteries, still can have a very powerful motor, and still clean much, much better than the single unit ones. And then the robot grapevine pruner is still in development, so we're going to finish that and then begin to sell it. And once we have that, you know, as you saw with the arm control, we'll be able to do other pruning and picking applications. Okay, so in my time in robotics, what has limited the deployment of robotics, the limiting factors have changed. You know, I showed you that chart in the beginning. Previously, the limiting factors were the processing speed per dollar. Sensors, you know, cameras and other sensors were still bulky or not very high resolution and expensive, and to some extent batteries, you know. But really, those have all been overcome. I mean, I have not run into an application where I didn't have enough processing power. You know, now we're sort of looking at downsizing processors at this point. You know, just using a nice Snapdragon as opposed to high-end Intel. You know, it's fast enough. Cameras, they hardly cost anything anymore, and batteries are, you know, have far higher capacity than they used to. So now, you know, we also do consulting, and when we go into various, look at various applications, what's constantly limiting us are the hands especially, and to some extent arms, and a little bit dealing with uneven terrain, stairs and split levels and stuff like that. But really, these two are killing us. I mean, the human hand is just amazingly good at everything. You know, I mean, it's fast, it's powerful, it's flexible, it's tactile, it's adaptive, and nothing they have in the robotics arena comes even vaguely close to the hand. And then arms. Our arms aren't great either, but what I want is a 10-foot long arm that weighs nothing and it's very powerful. You know, I'm the software guy, and my partner's the mechanical guy. I keep telling him that, and he keeps not delivering. So anyway, the future of robotics is the hand. Anybody can invent. And it doesn't have to be a hand. I mean, think outside the box. I haven't been able to think of it, I have to admit. But I mean, there's got to be some way to rapidly, gently, and adaptively grab stuff. I mean, if you just look at all of the stuff in agriculture and industrial automation, it's like stuff is coming at you, and you just got to be able to grab it, you know, and you got to be able to grab it gently. And it's just, It's just not happening. That's my frustration. And I'm asking all of you to go home and invent a hand for me. Very simple. So, yeah, as I say, basically, if we look at a lot of automation, there's some cool stuff, and where they do grab stuff. But what they do is, because the hands are so crappy, they have all these conveyor belts and stuff to space stuff out, and really expensive arms, and it's all custom design. It can't be used for anything but what you're using it for. And so that means expensive, and expensive means you can only do large, high-volume application. But the thing is, there's a gazillion niche applications. Like somebody wants to sew something on something, that you just can't go through this whole custom thing. But if you had the flexible hand, then they could all be addressed. So if we can get a human or even monkey-capable hand for less than about $10,000, it's really, literally trillions of dollars of applications that would be commercially viable right now. Again, they're all niches, but there's millions of them. So, I'll talk about this, I think, next slide or the one after that. Yeah, sure, a few jobs may be in danger, but, we'll have to worry about that when the time comes. So, and just a bigger application that I just want to kind of leave with you for the whole hand thing is, how about robot butlers? You don't see any. Well, why not? Well, I guess they'd be kind of expensive even without the hand, but not really anymore. I mean, again, a $50 Snapdragon chip is good enough for a robot butler. Siri is good enough for a robot butler. Vision, I can make you a robot butler and you can get around the house for not that much money, but it can't do anything because it doesn't have hands and arms, So I mean, because just consider, go get me a cold beer, and or chop the zucchini, and how hard can it be? Well, it's actually remarkably hard if you don't have hands. Like, let's consider the steps of going to get a cold beer. Let's assume the kitchen's on the same level. And the refrigerator's in the kitchen. So the robot goes to the refrigerator, and well, he has to grab the door, and he has to put a fair amount of force to open the door. And so now he's inside the refrigerator, and well, the beer is behind a package of lettuce and some zucchini. So it has to, and each of these have a different shape, and it has to reach in and be able to grab the lettuce bin one way and the zucchini package the other, and it has to do it gently. It doesn't want to squish the zucchini, that would be bad. And so now it's finally got those out of the way, and now it can go grab the beer. Well, who knows what angle it's at, so we have to have a few degrees of freedom there, and it's glass, so we don't want to crush that, but we also don't want to drop it because we don't want a broken bottled beer all over the floor. So now we pull that out, and we have to put the lettuce and the other stuff back, and now we can close the refrigerator. And finally, closing the refrigerator is something you can do without a hand. Yay, one thing. So now we take the beer over to the drawer that has the beer opener in it. Well, we have to open the drawer. Well, it has a different kind of handle that's going to require a different adaptive sort of hand thing with a different sort of tactile ability. And it's going to open that. And now look at that. The beer opener is under 3 knives and 2 other things. So it has to pick those out of the way. And now it can finally grab the beer opener, and then it has to grab it the right way, orient it the right way, grab the beer bottle, open it. Now let's go find a glass. Anyway, on and on and on. You get the idea. So a butler or a personal assistant or an elder caretaker, enormous market. I mean, we'd all love one, right? And it's for people who are elder and stuff like that. They're almost becoming, a necessity if they're going to stay in their house. Enormous market. Without cheap, good hands and arms, you're not going to see them. And that's why you don't see them. So invent hands. Okay, so one thing we have to realize is that jobs are potentially at risk. What we're seeing and what I'm seeing is that every day there's more and more stuff that my robots can do that take away jobs. You know, it's 5,000, so my lettuce thinner, for example, will displace about 5,000 people. And can they move on to something else? Yeah, probably, but then I might displace them there. So it's you know, it's kind of iffy. On the other hand, if you've ever tried hoeing all day in a lettuce field, I promise you, you don't want that job. So I'm not getting rid of any particularly good jobs. I personally love minimum wage laws because, to me, they're robot full employment acts. You know, in other words, I have trouble competing against somebody being paid $7.50 an hour, but $15 an hour, there's a lot more applications. So I just simply raise it to about $50 an hour, and then, you know, we'd really be busy. So I'm not sure minimum wage laws are a really good idea right at the moment if you're looking at jobs, but they're really good for the roboticists. So, I mean, right now, you know, I'm addressing, well, what can robots do? But in about 20 years, especially after the hand is invented, the question will be, what can't robots do? So, you know, there's going to be a lot of turnover of jobs, a lot of retraining that needs to happen. I'm wondering if at some point there'll be reprisals, you know. So, like right now, if you want to paint nails, you need to go get a license. Well, maybe robots are going to need a license for new applications or even a given sale, something like that. But what I'm sure is that robots won't take over the universe. And the reason I bring this up, and I'm sure most of you have seen it, is a guy named Nick Bostrom, who's a philosopher from Oxford, basically wrote a book called Superintelligence that predicted that the universe is going to be overrun by artificial intelligence. And he gives this example where a superintelligence is given the task of making paper clips, and it basically figures out how to transform the entire universe into paper clips. Well, and Elon Musk, you know, of Tesla and SpaceX fame, says artificial intelligence is humanity's greatest threat. Never mind nukes and, you know, design pathogens and meteors from outer space or electric cars that go way too fast or anything like that. It's artificial intelligence. That's their biggest threat. Yeah. And, you know, and there's been many others in the news, and it goes all the way back to the Luddites, really. You know, machines are going to be the end of the world. Well, for those of us who actually work in robotics and artificial intelligence, we know that it ain't going to happen. You know, Elon Musk is a smart guy, but he's not an artificial intelligence developer. Nick Bostrom is a philosopher who, by the way, wanted to sell this book, and he picked a very good title to sell a lot of copies. It did sell a lot of copies. So I could stand here for hours and tell you why it ain't going to happen, but I decided to pick just one reason it's not going to happen. And basically, the type of intelligence that's in our heads or would be part of some superintelligence, it's not programmable. We're not going to sit here ever and program that sort of intelligence. That sort of intelligence needs to evolve. And things that evolve depend on their environment. So if we say, well, humans are intelligent, at least some of us, you know, but what caused our brains to evolve? And our brains, you know, evolved because we had bodies that had a need. And those bodies have blood and breathing and circulation and hormones and all that stuff. Whereas robots will evolve to serve humans. That's what's going to drive everything a roboticist does. You know, lettuce thinners aren't going to suddenly take over the universe to thin lettuce. It's just not going to happen. I mean, so and then there's just one other area here. Some futurists, like say Ray Kurzweil, talks about, well, let's say we take a three-dimensional snapshot of Bret's brain, and then we simulate it perfectly. Well, you know, then we've started with a base of intelligence, haven't we? To which I say, no, I don't think so. I think that if you took a snapshot of my brain and simulated it perfectly, you'd have Bret in a coma, because I don't have the blood, breathing, all these other things. The brain serves the body. It's not the other way around, you know. So last thing I say is, the other reason it's not going to happen is because intelligence is overrated in robots. Robots don't have to be particularly smart. Siri is not particularly smart, but she's good enough. You know, my vacuum cleaner, which looks kind of cool, there's no smarts in that. It's all kind of models and stuff like that. So there's no drive to do this intelligence thing from a commercial standpoint. Maybe some massive effort in universities will, work towards it, but they don't worry me quite as much. And so that's it. So now it's questions.
So I got like a million questions I'd like to ask you, but I'm going to try to be nice and let other people have a chance to just ask me one.
Okay.
I've been investigating the use of robots to grow food for a while. I've seen a lot of really interesting patents that have been applied for. I'm curious, in your work in developing a robot that works in agriculture, have you run into patents? Have you run into something where you've said, oh, we want to do it that way, but they already got there?
So our single biggest innovation is probably the concept of scouting. In other words, figuring out what's going to happen before the actuators get there. That was not patented, we patented it, so I'm not going to run into that one. If you look at the concept of using an arm to do something, those patents are all expired. If you look at the concept of using vision to do this or that or the other thing, those are kind of old too. So there are potentially some roadblocks. We do patent searches for everything we do. So far, they haven't been a big deal. The lettuce thinner, that concept was patented, the whole thing, by somebody else in 1970. Patent's long since expired. So, nobody can really come after me for that one because I'm just using this patent exactly. So that's what we find a lot in robots, is people have these great ideas. Heck, I have these great ideas. I patent them, and then by the time they're implementable, the patent's pretty much running short. So that's now that may happen less because part of it was the whole processing thing. If you didn't have enough processing, you could have all these great ideas. You could know exactly how to do it, but you couldn't. You had to wait. Well, now, as I say, processing is not an issue anymore. So it could be that if somebody comes up with a hand, then...
So is it fair to say that the race is on?
I think the race is more on for patents and intellectual property now. I think the number of robot applications is going to increase exponentially from here. I think it has been increasing exponentially, but now that exponential is actually going to mean something.
So you said that we've been tracking processing power and exponential growth pattern. Were you saying the same thing in mechanics, and where are we at in that?
Well, so no, that's the problem. So the fundamental piece of most actuators is a motor or solenoid, right? And so I kind of look at those, and they're getting a few % better a year. So with the processing thing, basically we're getting a factor of 10 every 5 years. Here we're getting 20% in 5 years. So that's going a lot slower, and that's one of the reasons arms aren't getting much cheaper and stuff like that. So no, mechanical stuff is happening really slowly, but that's where, as I say, that's why I need this hand, and I know it's going to happen slowly. I know it might take 20 years, it might take longer, or someone might come up with a great breakthrough. And people have been thinking outside the box. There's one relatively clever gripper I saw. There was actually just a bunch of plastic beans inside of a bag, and it would just come over whatever you wanted to grip, and then would suck all the air out, and then the beans would go rigid, and then it could pick it up, and you let the air, and it would drop. So there are people thinking out of the box, and there may be something really clever like that can make actuators cheap and reliable. But right now, that is the limiting thing to me. I mean, we go out and we consult and we talk to people, and if I just had that fast hand, there'd be so much more we can do.
So when you're making those 3D models of everything, are you relying solely on stereo cameras, or are you using other sensors as well, or multiple stereo cameras and getting different angles?
So the vacuum cleaner is just stereo vision. The grapevine pruner is just stereo vision to make the model, and then it has those lasers to help line up the vision, but that's not actually, you know, used for modeling. The lettuce thinner is actually just mono vision because everything's on a flat plane. So yeah, we pretty much stick to vision. The one exception was we also did some work for the Department of Defense, and they basically wanted to take the vacuum cleaner concept and put it on a single unit, and it basically looked like R2-D2 and operated kind of like R2-D2 too. And it had 4 sets of stereo cameras, but also had a LiDAR, which you could use or not, and it had an IMU, you know, inertial motion unit. So all of our software can take any sensors. We could put ultrasound, etc., but typically we stick to stereo vision. We have played with the new Microsoft Connect and its time-of-flight cameras, and that's pretty slick, but we haven't deployed it in anything yet.
What does your software stack look like?
So, yeah, the thing about having started in 1999, things like ROS didn't exist yet. Even OpenCV didn't really exist yet, and so all of our software has been built in-house. It's all built in C. It's all very modular. Typically what we have is the application subtree, and then we have other, like a common tree, a vision tree, a camera device tree, and stuff like that.
So it's basically a common platform across products.
Yeah, so if you look at the shared software between a grapevine pruner and a vacuum cleaner, probably something like 80% is shared. Because you know, vision is vision, and geometric manipulation is geometric manipulation, and matrices are matrices, and stuff like that. So it's, yeah. And in fact, the lettuce thinner, the last thing we did, you know, we put that together from the time the grower decided they wanted it to when its operational field was, you know, less than 6 months. That included all the software and all the mechanical. So it's very, very modular and easy to apply to new things.
You mentioned on the vacuum cleaner that it does some mapping ahead of time?
Yes.
Is that autonomous?
Yes, yes. So yeah, the operational concept is you plug in the vacuum cleaner, it turns on, it looks out into the world and says, do I recognize this? And if the answer is no, it then begins to do a frontier exploration thing to understand the environment it's in without vacuuming at all. And then once it's done, it turns on the vacuum and cleans away. If it wakes up and says, oh, I know this room, that just goes off and vacuums.
So it's a library, it has a library of past experiences.
Yes, yeah, exactly. Now, you know, it doesn't have to match perfectly. You know, if this, well, this room would be a nightmare for it. I mean, the chairs are moving constantly. But most rooms, you know, are mostly stable, except maybe the kid left some clothes on the floor, or around the dining room table. It has to sort of remap because you didn't happen to leave the chairs in the same place. But 80% of rooms are the exact same way they were before, and the other 20% roughly, depending on the room, adapt.
Do you do any kind of a mapping into a standard 3D format, like file interchange format, where you can store it off and communicate to some other robot, a model of the world, so to speak? Well,
yes and no. I mean, so the vacuum cleaner and the grapevine pruner and some other stuff use some sort of voxel grid, occupancy grid. So it's not really understanding that this is a table, but rather I don't want to bump into that leg, and you know, it knows where there's stuff and where there's not stuff. So to turn that into, we turn that into like a VRML, so virtual reality markup language, which we then can display. We can turn it into polyhedrons and meshes, and we do that sort of thing. But we don't necessarily have one standard package that we do that with. We have lots and lots of visualization tools because it's pretty much impossible to do this stuff unless you can see what's actually happening.
So how much simulation do you do in development prior to actually building something, and then actually do you use simulation to control it? Is that part of it?
Yeah, huge amount of simulation. So for the vacuum cleaner, well, for every robot, but let's focus on the vacuum cleaner for a moment. We actually have a library of virtual rooms, which are in this virtual reality markup language, and that we can run it in. And basically what that means is instead of the actual cameras feeding us images, we have OpenGL feed us rendered images, or POV Ray if we want more realistic detail. And then instead of actually actuating motors, we send the actuation commands to something that says, well, if that actually happened, the unit would move to here. And so the software has no idea if it's in a simulation, in a virtual reality or real reality. It just has either virtual cameras and motors or real cameras and motors. For this sort of development, that's incredibly key because, first of all, before you build it, it's less so now, but 15 years ago when we were doing this, before you built it, it took a long time to get anything built. It was very, very expensive. We couldn't just print it on the 3D printer like we do now. You want to have a kind of an idea that it was going to work, and so we build all this stuff completely in simulation. And then when the real robot would show up, we'd figure out what the differences and how it moved, and our simulated robot moved, and we just update the simulation. And that way each engineer could have as many simulated robots as they wanted, working in as many environments as they want, even if we only had one actual robot. So yeah, we use a huge amount of simulation.
So what was the time? So let's say on the Grape Pruner, you had a simulation running, and then you go and actually deploy it or field the unit, and then there's got to be, you're calibrating to reality. So there must be some tuning that goes on to.
Okay, so yeah, I'll answer that, but let me just first describe a little bit about we also have sort of this halfway simulation mode. So the Grape Pruner is out in the field, and it's collecting images, and it's doing whatever it's doing, but it saves all those images, and it saves all the sensor data. So then later, when I'm sitting in the lab, I can replay all those images into the software, and I can make tweaks and see what happens. And for the front part, which is just modeling, whatever tweaks I make doesn't affect anything. Unlike a vacuum cleaner, if I was modeling the arms, which you can also do, a tweak will change what happens, and therefore you can't really do that quite as effectively. But yeah, so we also have this replay mode, which is sort of half simulation. We're taking the sensor data from the real world, but then we're running it internally in a simulation mode. So what was it now?
Well, though, so I'm just, the day you go to the field and you actually try to get to work, and you have the simulation, you have this middle step, and then you must have a user interface for dialing it in.
Yeah, exactly. Well, so for the Grapevine Pruner has been under development a long time. So in the beginning, we take it to the field, and it didn't work at all. I mean, basically not even close. We at least had the images, and we could go back and at least get the model kind of right. But it's like in the beginning, the robot arms just simply never got near the canes. It took a while to figure out why that is, and it turns out, well, that's because the front cameras are pointed, the modeling cameras are pointed one way, and the arms on the robot, or the cameras on the robot, are pointing a totally different way, and everything's moved, and so there's this huge synchronization problem. So yeah, the very first time we took the robot vine pruner out to the field, didn't cut any vines at all. Not one. Sheer luck. I would thought I would get one, but yes. So yeah. So then, well, what's wrong? So we have to do some real debugging on the real machine, and we both fix it and feed back the difference between the simulated robot and update that as well, so it matches as close as possible.
How big is your software group?
Well, so that's kind of an interesting question. Right now, the software group is 2 of us, and at one time it's 15 people. And part of the reason for that is, I mean, it's really an extensive software base, and there's really not that much to do anymore. As we approach new applications, I may hire some people. But as far as extending the lettuce thinner into a weeder, there's not enough software there to really even be 5th time, really. And the vacuum cleaner, well, that's kind of done, so now it's more building the mechanics and testing, and we'll extend that a little bit, but 2 people is enough at the moment, maybe more again.
So what about making money? Do you license like the design and someone builds the volume units?
Well, so the lettuce thinner is currently the only actual product that we build and sell, and what we do is we subcontract the manufacturing of the hoods, and we buy off-the-shelf cameras, we buy off-the-shelf cabinets, off-the-shelf computers, and we do final assembly at our little tiny place. It's not real high volume, so you know, we basically finish one and ship it off, and then finish the next one, and so.
Would you see a time when John Deere would take this on as a huge part of their?
Well, we've talked to John Deere, and John Deere probably not. John Deere told us to come back when we're selling $100 million a year worth of lettuce thinners. And they're a $40 billion company, and so 100 million is a roundup error to them. And if it's smaller than that, you know, that's noise. They don't want to deal with noise. So, and that's kind of true of Toro's smaller, but the huge ones aren't interested in the specialty crop sort of robots. But there's a whole bunch of regional ones. I don't know if you've heard of Oxbow, and you know, so they will sell $10 million, $5 million worth of a given product. And so there's people we've talked to who are more likely. John Deere, and they also have a tremendous not invented here attitude. So you know, we'll keep in touch with them, and you know, if for some reason the weeder actually sells that much, we will certainly let them know.
So also recently, John Deere had that whole everybody getting mad at them about not being able to fix their stuff because their equipment's under software, and they.
Yeah.
Have you guys run into anything like that at all, where people are wanting to be able to repair stuff, like this is our software? How do you kind of deal with that whole situation?
Well, so if the software were breaking, it might be an issue, but the software is actually pretty stable. We haven't changed the lettuce thinner, except for a couple minor tweaks in a long time. So one thing we do for the farmers is that we make as much off the shelf as possible. They have a huge spares kit. They quickly learn how to fix stuff. You know, we train them how to see if a camera is burnt out or something like that, and how to replace it. And then for things like you know, the solenoids for the sprayers and stuff like that, they deal with that stuff all the time. So typically the guy running the thinners, the foreman guy, does lots of fixing on their own. If they do need a software issue, they call us. That hasn't happened much. Sometimes there's a failure that is, you know, a couple failures on top of each other that he can't quite figure out. Then he calls us. We're able to actually log in from the office. Basically, he has a little broadband modem. You tell him to plug it in, and it dials in. Since it doesn't have an IP address, it has to dial into us via tunnel, and then we just connect up and we look at the logs, and you know, we help them out. So that's how that works.
What does your hardware look like? Are you on PCs or?
It's all Linux. It is, I guess, right this second, all Intel. I think 3770K i5 is our favorite one. But as I said, for the lettuce thinner, what we're planning on doing is each hood will have its own Snapdragon probably, and the vacuum cleaner will be Snapdragon based as well. The vacuum cleaner, because it's battery powered, you want to have low power, and so a cell phone style processor is kind of the better bet. Intel processors are, you know, have done well for us, but they typically suck down a lot of power. So
do you make use of any of the RT stuff, or are you just purely on the kind of near real time?
Yeah, it's near real time. I mean, we use you know, the real time scheduling extensions, and we use memory lockdown, and we do some other stuff.
Keep it lean.
What's that?
You just keep it lean.
Yeah, just keep it lean. Yeah, and make sure there's more than enough processing. It seems to work well enough.
Cool, great. Well, thanks, Bret, for your time. Appreciate it.